Okay, welcome back. Yeah, if you find time to look at the lecture files, would be great. There's probably more information than we could say here, and maybe you find new questions or answers to the questions you had, or otherwise, if you happen to look through them, just come back to us, and we are happy to answer your questions if we can do so. Okay, today, the next topic I would like to talk about is multi-planet systems, and this contains the following topics: resonances, dynamics of objects, and circumbinary planets, and systems of several planets. Okay. So concerning resonance, I will give only a very, very brief introduction to resonances. This would be a whole full-fledged week-long lecture series, I think, talking about resonances. So we start out from the solar system, and we have there two planets, or one planet and one former planet, Neptune and Pluto, and they are engaged in a 3 to 2 resonance here. That means while Neptune is performing 3 orbits, Pluto is performing 2 orbits. This is called a 3 to 2 orbital mean motion resonance. Okay. So the period of Neptune was 165, Pluto 248. If you divide this, you have roughly 3 to 2, and the distances are 30 and 35 AU, basically, from the Sun. And here's the orbit plotted, the outer planets only, Sun and the outer planets here. Here's the orbit of Neptune, and you can see the orbit of Pluto is a little bit further out. Not only that, but it's crossing the orbit of Neptune. It's sometimes inside the orbit of Neptune because of its eccentricity. Yeah. But then in addition, this orbit is inclined a little bit, which is not shown here, of course. It has I think, 17 degrees or something. Don't quote me here, inclination here. But nevertheless, the orbit so close here, or the eccentricity is so high, 0.25, so that that Pluto can be inside even of Neptune's orbit. And potentially, as you can imagine, this can cause problems if they were on the same plane. This is problematic since they would come very close to each other and possibly collide and become unstable. Okay, and this is prevented. This instability, in this case, is prevented by the existence of this resonance. Okay, so resonances can, in certain circumstances, not only be stabilizing, as, for example, you might have experienced or tried to experience when walking on the bridge over the glacier. If you jump down a little bit and bring the bridge into some oscillations there, and you happen to hit the resonance frequency of the bridge, this would lead easily to disaster. Okay? But this is then a destabilizing resonance, and in this case, it's sort of a stabilizing resonance. I will come back to this. Okay? And of course, the most interesting bit, which is on this diagram here, you have already noticed this: new horizons at Pluto on the 14th of July this year. Okay, and then we may be able to see more what Pluto actually is all about. Okay, the point here is that in this 3 to 2 resonance with Neptune, there are many other objects. This basically the same orbit as Pluto. And this fact, after all, led to the degradation of Pluto and becoming a dwarf planet instead of remaining a real full-fledged planet. Okay, so why is it, in this case, stabilizing this resonance here? It's stabilizing because the orbits are laid out such that they avoid close encounters. So there's always a minimum distance that Pluto and Neptune can have, and this is only guaranteed because the system is in resonance. Then you can make the orbit such that they never come very close physically, the two bodies. Okay, so Pluto basically maximizes its separation from Neptune, and this is only possible because it's resonance. So this is here in this animation here. I said first what you see here different planets. This is Pluto, pinkish. This is Neptune, and we will be seeing this movie in the co-rotating frame with Neptune. Okay, so Neptune will not move much in this movie. We are in the co-rotating frame with the orbit of Neptune. And then we have Uranus here, Saturn, and there's another planet there. Okay. Nice, hmm? Okay, we can see this is the orbit of Pluto in the co-rotating frame with Neptune. And you see there's always some separation here. They never get very close, even though the orbits formally cross each other. Okay? And this is only possible because you have this 3-to-2 resonance, and then you can clearly see if one object is doing 2, the other one is doing 3, and they always are separated well enough when you hit this resonant condition here. So this is here a stabilizing situation here, okay? Stable resonance. Good. So what is a resonance? And you don't read all of this here, okay? You only read the red part here, okay? The mean motion resonance is given by an integer ratio of their mean motions n. So you assume that these planets move with a constant velocity through their orbit. Yes, and this you call the mean motion. And they divide those mean motions here, or you divide the periods, basically. It's the same here. You divide the mean motions, the mean velocities here. And this is if this is a ratio which contains 2 integers here, that means those are part of the normal natural numbers, then you have a mean motion resonance. There are other resonances. This is why we have to distinguish this here. There are resonances, for example, secular resonances when the apsidal lines, if the planet moves through the orbit and the direction of the periapsis moves with time, and if you can also have their resonance between different motions of these apsidal lines. So this would be a secular resonance here. But we are talking only about mean motion resonances, and you can define very complicated things and actually mathematically make a more stronger statement there. Here, all of this you find in this book, Solar System Dynamics by Murray and Demotte. Okay, so you didn't read this, of course, and we do not read this here as well. Only one thing, you can get a more formal handle on this by expanding the perturbation potential between the 2 planets in terms of a Fourier series, and measure the importance of the different terms there. And from there you can mathematically show under what conditions are these planets in a resonance or not. I will just give you the example here. Was here something interesting down here? No, not yet. Okay, give you 2 examples how this looks like. Okay, this may be more illustrative. These are 2 real examples of extrasolar planetary systems. My most favorite system, or it used to be my most favorite system, now I have another most favorite system, but this once was it GJ876, okay? It's a system where you have a star and 2 planets, and these planets have periods of 30 and 60 days, and you can clearly see this is 2-to-1, okay? And the interesting point is this is an M star, a 0.3 solar mass star, and the planets are very massive. Yeah, so this is amazing because lower mass stars, as we have seen, have typically lower mass planets, but this is the big exception. The planets are several Jupiter masses, basically, in mass, so they are very high for an M star. And the point is they are in a very nice 2-to-1 resonance, and this is depicted here. You can see the inner planet moves exactly twice when they hit this line here, and this is the apsidal line. So this is the periastron of the inner planet, periastron of the outer planet, and they both are here, tuck, and the blue one makes 1 orbit and the other one makes 2, so this is the orbital configuration of GJ876. Okay, it's very nicely in this resonant configuration, and you can see also that these 2 apsidal lines here are always aligned. This is what we call apsidal co-rotation. I thought I spilled my coffee now here, but it's not. Okay, this is called apsidal co-rotation. Okay. Good. That's this movie by Man-Hoi Lee. He produced this. Okay. So that's this one here, apsidal co-rotation. Okay. And then we have this system here, HD128311. and the ratio also sort of 2 to 1. Okay, it's not such a clean case as this one here. This is the clean. I think this is the cleanest case of a mean motion resonance you have in all extrasolar planetary systems. So this is the paradigm case, basically. Okay, all other cases are not as clean and nice. So this is the other one, and you can see the same thing. You don't see the planets moving here. You only see the changes of the orbits of the planet. Of the planets, okay? The star is here, this is the inner planet, the orbit of the outer planet. The actual locations are not shown because they would just move very rapidly here. This is the periastron of the inner planet, periastron of the outer planet, and you can see it's quite a bit more complicated, okay? The inner planet is a little bit more eccentric here, so you always have a well-defined periastron. The problem with the outer planet is that sometimes this thing jumps here, and the reason is that the orbit becomes circular once in a while, and if it's circular, it does not have any eccentricity, okay, for one, but secondly, you cannot define the direction of periastron for a circular orbit, and so it can change from a point to an arbitrary different point, and that's what's happened here. Okay, that's why it jumps sometimes. When just before it jumps, the orbit is very circular, and then it suddenly jumps when it's circular to another point. Okay, because the eccentricity of the orbit of the outer planet goes to 0 at certain intervals. Okay, so this is a dynamically quite different system. The eccentricities of the other system, GJ876, they're very nice. They are very constant, so they don't really change in time. Well, this system here does it, and here it's so that of the resonant angles, which was all mentioned in gray, okay, one of them is circulating, and this is the problem here, while here both of them are librating. So this is the mathematical reason for that. Okay, details you find in those papers. So then in the Kepler system also we have many, many planets, and you can compare the period ratios of those planets and look if you have resonant planets amongst the Kepler planets here, okay? And indeed you find at certain resonances, 3 to 2 mean motion resonance and 2 to 1 mean motion resonance, you find that there's an overabundance of planets in those locations, yes? And not quite at the resonance, but just outside of the resonance. And there are several theories here. One theory is that this is comes about due to tidal interaction of these two planets with the central star, but there are other possibilities here. So we have an overabundance here of 3 to 2 and 3 to 1 resonances in this distribution here. So this is basically the period of the outer planet divided by the period of the inner planet, okay? P2 divided by P1, which is plotted here, and here just the number of systems here. Okay, so they're slightly outside, but it's nice that you have this at 2 to 1 and 3 to 1, you have these. Why is it so interesting to look at these resonances, and why is it expected in a sense that you have an overabundance in those locations, that it is not spread out evenly here? And for that we have to look at the origin of these resonant systems here. How do you form a resonant configuration? Okay, for that we look again at the disk-planet evolution here. We have a disk here, and we have two relatively massive planets. In this sample case here, 2 planets here. And these planets are so massive they have opened up a gap, so they have a joint gap, but it will work also for smaller mass planets here. And then the planets experience different migration speeds. This is the whole story about capturing resonance. You see, if one planet is orbiting very nicely at this location, here's the star, orbiting the star here, and the other planet outside migrates faster than the inner planet. So the outer planet will keep up with the inner planet here, comes ever closer here, and then it can happen that they're in a resonance configuration, okay? And then they will get excited, okay? And we'll come to that. So they join, and then a large gap here, and so the outer planet moves in because the outer disk drives it inward. The inner planet stalls or moves slightly outwards because of the inner disk here, so they will approach each other. The planets get closer. And this is the whole story. You can have this with differential migration speeds. The planets approach each other. You have a convergent migration scenario. I should have written it down here somewhere. Convergent migration. That's the key word here. Okay, separation reduction. That's the same after all. And then you can get into a resonant capture. So what happens if those two planets experience some resonance? There's possibly 3-to-1, 2-to-1, or 3-to-2. And as we have seen previously, 2-to-1 and 3-to-2 are the most likely outcomes of this thing, which you also see in the numerical simulations, by the way. Okay, what happens if you actually get close to this point where you are in a mean motion resonance here? So here we have this situation. This is our most beloved system here. So you have two planets here starting at some distances here. This is the semi-major axis. This is these blue curves. And on the right-hand side, we plot the eccentricity as the red curves. So this has semi-major axis evolution and eccentricity evolution in the same plot. Don't worry, okay? So we go first with the semi-major axis. So initially the planets are put into the disk, and we wait until everything is nicely in equilibrium there. And then the planets feel the disk, and they begin to migrate inwards here. And they capture each other in the resonance here, so they will migrate at the same speed basically inward here, and is such that the ratio of those two, A2 over, or the period ratio I should say, of these two planets is in a 2-to-1 mean motion resonance here. So you generate this, but by a natural migration scenario. At the same time, when they get into this resonant configuration, the eccentricities are excited. Okay, this is quite natural. Because you have to imagine you are sitting on a swing, and somebody pushes you always at the same time. You get excited. The amplitudes get higher and higher. And if the amplitudes of this is also periodic forcing. You always meet at the same location there. You always get at the same location a kick. We have seen this in GJ876. You always meet. When the periastrons are aligned, you always get a kick at the same position, and you excite the eccentricity of the two objects while maintaining the resonance. Okay? So the eccentricities are getting excited. The outer planet is more massive, I think, less excited, the inner planet more excited. And these horizontal lines, interesting enough, you could have imagined those are the observations. So these simulations by Orion, who has done them, Orion Krida, show how you can obtain a system like GJ876. But the whole procedure is generic. That's why I'm showing this here. Whenever you capture in a resonance, you excite at the same time the eccentricities of the two objects. And if you're lucky enough, you have found the right conditions for the disk and such, then you can even match the observations. But this is a playing around with parameters a little bit, with the disk mass, with the planet masses initially, yes. But you can get roughly the correct eccentricity. If you include all in the simulations, let's say the eccentricity damping automatically comes out of the hydrodynamic simulations here, and they give automatically here the right answer roughly. Okay. Good. The most important thing for the future discussion, subsequent discussion, is the excitation of eccentricity. So you compactify, that means you get closer together, convergent migration, and you excite eccentricity. This is what these two keywords mean here. Okay. And then this was all about resonances, okay, very short and clear. Now we come to dynamics, okay. So we want to understand the high eccentricity, for example, the high eccentricity distribution of planets and or the inclination distribution, okay? But I only show this picture here, the inclination picture is somewhere else. So this is the orbital eccentricity of the observed planets here versus separation from the star here. And this is in color, you have also the mass of these planets here, okay? So we can see these exoplanets have very high eccentricities. If you compare this to the solar system, which is very different, okay? In the solar system, they're all lounging around here in the bottom here, and here we reach even, I think, 0.93 or something. This is the highest eccentricity that is observed. I will come back to that system here later on. And the question is now, how do you make these eccentricities? And there, partly what I've said before plays in one explanation scenario here, a major role here. So how do you make this? Because as we have seen, the problem is that as we have seen, the evolution in a disk, planets are formed in a disk, and the subsequent evolution in the disk tends to damp out the eccentricities of the planets. So how suddenly they get excited again? Yeah? Because initially, during the early growth, they will have been probably in nice circular orbits with very little eccentricity and very little inclination. Okay, and how do we get to this situation? So, eccentricity and inclination, but yeah. So what can cause those high observed eccentricity and inclination? I did not show the inclination picture, but you may have heard about this in some talks or in the media even. Okay, there are in principle two models that I would like to mention to you now. There's one so-called related to a scattering process, and this comes about, you have differential migration of planets in the disk, as I've just shown you. Okay, the configuration becomes compactified. The eccentricities rise during this compactification process, okay? And then suddenly, or the following, the eccentricities can become very high when they approach each other. And the disk is still there. In the disk, you have to is acting as a damping agent. As we have seen, the disk always tends to damp eccentricities. I've mentioned this yesterday briefly. The presence of the disk tends to damp eccentricities. So you have two actions here. The resonant configurations with the convergent migration process, the migrating inwards, try to increase the eccentricity. At the same time, the disk is damping the eccentricity, okay? But the disk dissipates at some point, and when the disk dissipates, and you are left with a system which might have a high eccentricity without any damping, and this may be unstable. Okay? If the eccentricity is too high, then you don't have a stable configuration anymore. There's a limit to the eccentricity, to the maximum eccentricity you can have. Okay? So you take away the disk, and that reduces the stabilization. The instability of the planetary system ensues. You get excitation of E and E, you get gravitational scattering processes, and one of the planets is dumped inside, for example, produces nicely eccentric orbits, for example, and also close-in orbits, for example, which are eccentric or even inclined. They can be even, by this process, you can also produce inclined orbits. Okay. The second option, which is very nice as well, is tidally driven migration. I will come to this in a moment what this means, by the so-called Kozai effect. There, you assume you have a third body there. You see you have, here you have also more bodies, of course, but here you have, let's say, a star and Jupiter and another third object. So you have star, Jupiter, and one third object, okay? For example, a second star here, okay? And the star, the presence of this binary star can excite under certain conditions, large inclinations as eccentricities in the system. This is what you call Kozai mechanism, sometimes called a Kozai resonance, even though I'm not quite sure whether this is really a resonance in the classic way. Okay, that's why I call it Kozai effect or Kozai mechanism here. I will come to this in more detail, that's why I don't say anything more here, don't write anything down, this will be explained in more detail. So the first process here leads to the following systems. All right. You assume a priori that the evolution of the system has gone through a stage where these planets were embedded in the disk, and differential migration is a very natural process. So if you put a number of planets in the disk and follow their evolution, you will always see many, many resonances, much more resonances that are actually seen in the observation. So the major problem is not to explain why there's a spike. So the major problem is to explain why there are so few spikes. Okay, this is really the problem, because the planets don't move at the same speed, and if they don't move at the same speed, they will always capture into some of the other resonances. So this is the whole point. Okay, and you assume this with that you had this situation here. You have some planets which are very close to resonances or even in the resonances, yes, and then they are very a little bit excited already with some initial eccentricity distribution. You take away the disk, the system becomes unstable, and you perform pure n-body simulations of these unstable initial configurations. Okay, this is the procedure here that has been done already by Jovic and Tübingen in 2008, and then also more detailed by Bourget and Nesvorny here. And just to make I will not explain this plot in detail, but by doing so, you can excite eccentricities for one, you can excite inclination for two, and they match the observations which are shown here by these thick squares here rather well. Okay, this is the short answer to a long story. So you can get relatively decent agreement with the eccentricity distribution of close-in planets, and as Jovic and Tübingen have shown, with the eccentricity distribution of planets which are even further out. Okay, so this is the so-called scattering scenario of between the two planets, the dynamical interactions between the two planets that get these eccentricities excited. Okay. So this is inclination here. You can see you get to very high inclination. This is eccentricity here. Yeah, so these results match the observations rather well, and you can look for more details here. Okay, what is COSI? I think I do this before the break. Hope to get through this. COSI mechanism. Here you have, as I said, three bodies here. You have a star. You have here a second body and a third body. And now we have for this, it was derived for the solar system. And here M0 was the sun, M1 was an asteroid, and M2 was a larger perturber, Jupiter. Okay? And as you can see, you are now here in the plane. This one is the plane of the asteroid and the sun, and Jupiter's plane is inclined to this. So you need, that's the essence of this mechanism, an initial inclination of the orbits. Without that, it doesn't work. Okay? If you just put everything coplanar orbit, this mechanism doesn't work, but it works when you have reached a certain inclination I between these orbits. And in our case, we are looking for the excitation of the eccentricity of a protoplanet. It's the following here. M0 is the star, M1 is the planet, and M2 is the secondary star. Okay, this is the translation to our circumstances. Okay, and the most interesting thing is, if you look at the orbit averaged equations, so you integrate this whole system and you average the equations of motion over many, many orbits, then there is a constant of motion, which is the z component of the angular momentum, which is proportional to this quantity here. So this is a conserved quantity here. And you can see you can either change I and E. If I gets changed, you can change E. So E and I can oscillate. And you leave Lz constant during this motion. Okay, that's the idea. I cannot explain how I derive this equation, unfortunately. Okay, good. And this has been developed by COSI in 1962 already for the solar system, asteroid, Jupiter, and Sun. And this is the citation rates for this COSI paper, which is very interesting. Okay, so it was published in 1962, which is here. This is time and number of citations. Okay, so this was publication date, and then so 25 years, nothing much happened. So don't worry if your paper does not get cited over the next 25 years. Yeah, so yeah. Just sit down, relax, have a few beers, and go skiing, and so on. Okay? Yeah. So you just lay it back here, and then suddenly it will go off at some time. All the papers suddenly shoot off. Okay? No, some of them at least. So this was, of course, here you can see 1995. Okay. They're the first planets with eccentric orbits were discovered, and then people looked into the literature, yeah, went back, oh, we have known this, there was something, yeah, just like with the MRI that Phil talked about here the other day, yes, people were discovering, Balbus and Hawley were discovering the MRI, rediscovering the MRI, and they looked into the literature, oh, Chandrasekhar, whatever, has done this in the 50s already, and so on. So the same story here, yeah, so, and this is always worthwhile to look into old literature, like I have done yesterday with Lynn and Papaloisi and so on. So it's sometimes interesting to look what these guys have done, and it's nice. So, okay, it seems to be a very, very useful paper. Yeah. So what is it all about? Yeah. So we apply this now to this system here, and this is a little animation here. As you can see, this is the observations of that system. So highly eccentric orbit. and inclined with respect to the observation of the Earth. And I think they can do nice atmospheric studies of this planet here, yeah? Isn't it, Kevin? So, okay. So very interesting system. Yeah, it comes very close to the star, and it eclipses, I think, even the star. Yeah, is that so? Yeah, it has some eclipses there, so it's really very nice. Okay, period 111 day, mass, semi-major axis, eccentricity 0.93. This is, I think, the highest eccentricity. So people are always wondering, how does this system come about? Okay, how do you make it? Yes, and then they dug out this quasi mechanism here. And here the idea is the following. Planets tend to migrate from outside in, and through this quasi mechanism, they can obtain very high eccentricity. Yes. And when the eccentricity is such that this close approach is very, very tight, there's tidal interaction here between these objects that takes out energy of the orbit, and the orbit shrinks. Okay, here the migration of the planet is not induced by the disk, but by tidal interaction between the planet and the star. Tidally driven migration, that's the idea. You have the second star makes the eccentricity very high, up to 0.99, and then the planet comes very close to the star. You experience tidal forces. The planet will be distorted, the star internally will be distorted, energy is taken out of the orbit, a loss of energy means migration inward, okay? That's the whole story here. And they have modeled this. These guys, Fabricki, Dan Fabricki, and Tremaine, and at the same time, roughly a little bit earlier, even Wu and Murray have also looked into this problem. And I will just show you this nice movie here. So here you start out with the planet initially at 5 AU, so now we have seen it's much closer in, high inclination, reasonable eccentricity, and then you have a secondary star. Binary star parameters at 1000 AU, 1000 AU distance. So I would usually have said, well, it doesn't make any difference if we have a star that far away, but it does make a difference, okay? Usually would have said, no, there's nothing much that can happen. Nobody knows whether this scenario is correct or not, but it's very nice. That's why I like to show it to you. So here you see the following. Okay, see the following. Let's stop this for a moment. You see here this evolution of the orbits of this object. I know, I'm very familiar with this, sorry, but I want to finish this. Okay, so here you see the distance, 1000 AU or something, of the binary star. This is the binary star here, and the secondary star, and this is the star with the planet in there. Okay, frame of the binary companion here, okay, and the system we are looking at here is this system here inside, okay? 1000 AU, this is the scale here in AU. I hope you can read this. Okay, stellar spin vector here, planet eccentric orbit, the planet is in here, you don't really see it, okay? Now we move in, this is the orbit of the planet, this is the vector perpendicular here, the stellar orientation, and you can see how this changes in time due to the action of the secondary star, okay? It changes in time, this orbit moves around, yes, becomes sometimes more circular, and then speed up. Now we time in giga-years, okay? Tuck, 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 tuck. It comes very, very fast, several giga-years. You proceed this, and suddenly the eccentricity is very, very high, and then you get, it will happen, just watch out. We're beginning to move in, the orbit will shrink. Now we are still at the initial size of the orbit roughly, but then suddenly it will begin to shrink. Now it shrinks, you can see, small, and now we zoom in, and you are left with the planetary system as we see it now. That's the story. Okay, seen in this movie. Nice, you can look at this. It's on the page, I think, of Dan Fabricki, you will find it also. And this is in figures here, you have the oscillation of the eccentricity here, then you speed it up, duck, 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 then you suddenly have tidal dissipation with the star here, and then you shrink here, and this orbit is such, the evolution is such that these diamonds here are the present configuration we have. Okay, and you can judge yourself whether this is for your viable scenario here. You just capture it at the right time. After something like 3 giga-years, just short of 3 giga-years, you have the present configuration that you have now. This is the essence of tidally driven inward migration and eccentricity and inclination excitation. So by this mechanism, you can produce all types of inclination, obviously, and all types of eccentricities that you happen to have at the end of this evolution here. Okay. Good. This is time for a break.
you need, but that's good that you need. But I don't think you're going to get them.
Okay, I need to continue. Now, as you have seen, the observant eye has noticed that I skipped this topic here because there was some request that I talk about circumbinary planets. So I switched that and go first to circumbinary planets there. Okay, good. And this is only very brief. I have 20 minutes, I was just told, to explain this to you. So, circumbinary planets, what is this? So we have a binary star system here, and there are planets orbiting this inner binary star. I mean, here, you know this here, yeah, 2 suns on this planet here, famous observed planet. But you have more. You have more planets, and the idea is that, or what you observe is, that the planets are very close to the central binary. They're very close to the so-called instability region. I mean, it's clear to you, you have 2 massive bodies, 2 stars, and if you add a 3rd body, it will be unstable when it gets very close to the star. Okay, this is obvious, and but Holman and Wiegert have done a very extensive analysis. This is a classic paper, so you really ought to read this. So if the distance of the binary here is smaller of the planet from the binary is smaller than 2 to 5 times the binary semi-major axis, then the system will be unstable. And this is only 2 to 5 because it depends on the binary masses, the eccentricity, and so on. Okay, so that's why you have your some variation. So the good number is 3, by the way. Yeah, inside of 3 it's unstable, outside of 3, or pi maybe, outside of pi it's unstable, and so on. Okay, and these planets are all very close to this region. Yes, this is the observations. And the question is now, how do we get these? How do we make these planets there? Sorry, my ear is somewhat stuck here. Okay, how do you make these planets there? Okay, and we assume that the planets have formed further out in the disk, and then brought into this location by a migration process. There are several papers now, I will not cite any of those, that have shown that it's very difficult to make these planets in situ, because the perturbations of the disk are just too large. And there is not enough material there. There's always this problem. If you want to make planets very close in, you don't have enough material, it's too hot. But in addition here in the binary star, you have strong perturbations by the binary here to the disk. And so these planets will be even more difficult to condense, as we have seen it already in the solar system. There was this fragmentation barrier and so on. It's much more difficult here. So we assume they have formed further out, fewer UU distance here, and then we migrate them inwards. And this has been studied in a work recent by Arno Pierens, Richard Nelson. They have several papers there. This was the most recent here, where they looked at the Kepler systems. And I will concentrate here on Kepler 38. And if time allows, which it will not do, I will talk about Kepler 34. Okay, so what is Kepler 38? It's a binary star system, 2 stars, star A and star B, and a planet, small b, orbiting this. This is how you see it from the side, the top view, the side view. And we see the orbits are such, as you know, that you have an eclipse of the 2 stars. Star A eclipses star B eclipses star A, planet small b eclipses star A, planet small b eclipses star B. Okay, so we have 4 different types of eclipses there. And you can see them all in the light curve, and then you can infer the parameters here for that system. And then the question is, how do you get the planets to that location, and why do they park there? This is quite interesting. So, to do so, we need a disk. And I will present here some of the simulations that we have done with Nader Hagipur from Mumbai together. Okay, so a planet, a disk around a certain binary planet looks different from a regular disk. I will come to this in a moment. And you remember what Phil, who is not here anymore, said a few days ago. This is the central binary star here. The inner star, outer star, you see the Roche lobe of the outer star here, and here you see the disk material. Red is higher density, blue is very low density. Due to tidal interaction of the disk with the binary, or the binary with the disk, angular momentum is transferred from the binary to the disk, just like in the planetary case, and the disk recedes from the orbit of the binary and forms a gap. There's a huge inner gap in circumbinary systems. Okay, huge inner gap of the disk. So what will happen if you put a planet in there, which migrates towards the disk? So here you see the surface density. This is the standard surface density. Let's say you have a regular disk. If here at r equals 0 would be a single star, you would have something like this. This is now a little bit flat here, but the observations are something like r to the minus 1 or so. So this is even a little bit flatter here. So this is the surface density of an unperturbed disk around a single star. If we add a secondary star, the surface density goes down. You have this gap in the middle. Okay, you have a strongly different surface density here. Sometimes you see many papers that look at planet formation in binary stars assuming this type of surface density. This is, of course, not true. Okay? The surface density is massively changed by the presence of the binary, at least at the inner parts of the binary. And this here is in units of AU, I think, here. Okay, so we have a different surface density here, and it's perturbed by the binary, as you have seen in the movie, by the spiral arms in the disk. So if we add now a planet here, we added a 2 AU or something here. The planets migrate very happily inward here. There are different initial conditions. And then they settle suddenly to an equilibrium point. They don't go in any further. And the question then is, okay, where is this location? Where the planets stop? Can we understand this in terms of the dynamics of the system? And second question, of course, does this final stopping position agree somewhat with the observed position of the planet? And if it does, we say, yeah, fine, great. This is the solution of the problem, and we close it and go to the next system and try to find the solution there. Okay, and here one finds that the planet stops at the inner gap edge. I will show a picture soon with those orbital parameters there, and the observed parameters are very comparable. Okay. So at least the distance is very good. The eccentricity here is on the low side. I have to say, if you do an orbital evolution of the system here, you see that the eccentricity varies alone by the stellar interaction by much more than 0.03. So this is for some reason a very small quoted value here. Anyhow, okay, so we get rather good agreement. So this is a very, very good story. And here you see the evolution of the planet in the disk. So the planet starts out. This is radius. And this is the surface density distribution at different times during the evolution. So you first bring the disk into some equilibrium, you get the disk structure right, and then you put the planet in, assuming that it comes from outside slowly into the inner parts of the disk. You add it there here at 1.7 AU. You add it here, it forms a little gap, and it migrates inward, and it has a gap here, and it continues to migrate inward. So at this time it's here, at that time it is here, and then it ends up here. So the planet is parked at this strong positive density slope with the disk here. And it's clear the disk ends here. As we know, there's no more disk inside. So the planet here experiences here two types of torques. We know the planet will move according to torques. Okay, so are there any torques acting on the planet here? This is the question now. So we have the disk still outside. Yes, there will be torques, and the torques from the outside disk will try to push in the planet here. Yeah, this is Lindblad torques, this is spiral arms, as we have heard. But there's always material flowing past by the planet, and that material creates co-rotation torques which are positive. Okay? So you have also positive torques here, and this keeps the planet at that location. But the planet, it's also clear that since here's the edge of the disk, the planet can't be moved further in because the Lindblad torques will be weaker then. The planet has to stop there naturally also. But in principle, the exact position depends on this balance. This must be a zero torque position there, and that's why it's not very much inside, but a little bit at the edge, at the inner edge of this gap here. Okay, that's the present location of the planet, and this is what you see here. So here you find this, and if you look into this any more detail in this simulation, this particular one, you find that the planet is captured in the 5-to-1 resonant, actually, which is not good in this case, but nevertheless. Okay, so this is the final position. Here you see the planet moves around. It is on an eccentric orbit. Okay, and this is the line of instability as derived by Hollmann and Wiegert, 1999, this classic paper I have mentioned to you. Okay, Hollmann and Wiegert, 1999. Yeah, they derived this formula for the instability radius here, and everybody says when the planet is inside there, it's unstable. But you can nevertheless park it very close here, and you can see this parking position has been slightly too close. Okay, but anyhow, it's in this range here, and you can produce this here. Good. Shall I stop here or not? No, well, I can just give the summary here. But it's not the end yet, Mark, okay? I'm not finished yet. Okay. Kepler 38, circumbinding planets can be explained by a migration process. I think this is now the accepted idea here. Planets are parked near the inner edge, just outside of the instability region. And the exact location depends on the disk physical parameters. Okay, we would not have expected anything different, but I think this is a very natural outcome, okay, that many simulations show. The disk structure is not quite clear. The problems here is the disk structure, even without a planet. To calculate how the disk behaves without the planet is very difficult in the general case. Okay, and the numerical simulations, there are some around, but they are still tricky. There are some dependence on numerical issues, so still not solved. And of course, you would have to do this with radiation. We included some radiation here, but it needs to be done better maybe. And of course, you want to have 3D as real life. Does the same situation hold in 3D, not only in 2D? Okay, so I still have time, I think, to show the second system briefly, Kepler 34. The main problem is the high eccentricity. So this system was very nice. The binary star had only 0.1 eccentricity, but here the binary star has 0.5 eccentricity. And this is very perturbing, and I will only show one movie here, because this is so nice, I think. We'll show this movie here, and then you can just see what the problem is. This is the disk. This is the star here, the binary star. So you can see here it's highly eccentric, and it has a huge eccentric inner hole. Okay, and you can see there are lots of disturbances coming about here, and they are moving. Apparently, the spiral arm here moves periodically out here and generates this big hole here. And the problem is the observed location of the planet is somewhat inside of this hole. And we have not found any way yet to get this planet inside of this hole. Okay. This is the problem with eccentric binary stars. They create huge inner holes, and it's impossible presently. I think also Richard Nelson and Arnaud Perens have found that to bring the planet so close to the observed position into this case. This is the actual status, I think, of the formation of circumbinary planets here. And there's this system here, which is very nice because it's so dynamic here. Okay. And I want to stop here then. Okay, thank you. Oh, sort of.
He was short.
Just short of. Okay, questions. You are very welcome.
Studies seem to be showing that the abundance of circumbinary planets is about as high, if not potentially even higher, than planets around single stars. Can you comment on these sort of forming planets around binaries?
If they are so abundant, it must be easy. Yes, although the question is basically, the question was, the statement first was made that planets around circumbinary stars seem to be at least as abundant or even more abundant than planets around single stars. That was, I think, your statement. And then the question is, what does it tell us about the formation process of planets around circumbinary stars? And it's clear, it's not much affected, apparently. Okay, and why is this so? I mean, it's difficult, as I've pointed out, to make the planets there in situ. And people have tried this for a long time. And there are many papers, as you may be familiar with, that have looked into this issue here, and I will not repeat this. The main reason for that is that through the disturbances of the binary stars, the orbits of the embedded planetesimals will be perturbed. They will get very high eccentricities. And then you collide objects that have too high relative velocities, and typically you fragment, and you're not reaching, let's say, this barrier that you grow beyond a certain size. This is the main problem there that all these studies find, and this is not surprising in a sense, okay? And it is probably even worse because the disk is highly perturbed, which will even more excite the inclination of these, or the eccentricity of the orbits there. So it's even worse, I think, than these studies have shown, because quite often they assume a sort of quite regular, nicely azimuthal disk, azimuthally symmetric disk, and then they add just the perturbance of the binary star. But no, the disk is also very perturbed, as we can see here, and this leads to an additional excitation of orbit. So it is even more difficult. So the solution is, just like in the solar system and in many of the extrasolar planetary systems, you make the planets further out. I mean, the mass parameters of the planets in these circumbinary systems are very similar to the super-Earth systems, I think. Yeah, and we know they are very abundant. And it's also known that the super-Earth systems, this was the topic of the next part actually here, they are probably not made at their location in situ, so they have migrated from outside. I think this can be said. Yeah, they have migrated from a region which is, let's say, a few AU distance, and then they migrated inwards. And if you look at the eccentricity of the disk, for example, for both of these systems, you see the disk eccentricity here becomes very small for larger distances from the star here. Yeah? And this is in binary units, so this is it's around 1 AU, so this is very close. So you can easily make planets at several AU distance without any problems. And it's just like in single stars. Whether this leads to an observed overabundance of planets around binaries or not, this remains to be seen. But formally, I think the process of planet formation in circumbinary disks is very similar to that around single stars. So short question, long answer, sorry. But there are more questions possible. Sorry, please, how? Sorry, how large? I just didn't quite catch it, sorry. I have to apologize. So let me see this. How large is the rate of observed secondary companion in the system with eccentric planets? Oh, okay. Do we have, yes. So if this formation scenario of eccentric planets through the quasar mechanism is a valid mechanism, we should observe many companion stars around the systems. I'm sorry that I have to pass on this question. I don't know really whether you have many companion stars there or not. I mean, it's very difficult to get companion stars in that distance to the planet, to the planetary system. 1,000 AU, I mean, there are some known, yes, but it's very difficult. And I see Stefan raising his hand with the microphone, so he maybe can directly answer to that question. Okay, thank you. But I think around this star, I've shown here with 0.95 eccentricity, there is no secondary, or is there a secondary star? The one I have shown? Is there a secondary star observed? I don't think so. Huh? The one I have shown here. Yep. There is at 1,000 AU. Okay. Yeah. Okay. Thank you. There was one Sarah back there. The question is whether moons can affect the stability of resonance systems. Resonance systems, you mean in this sense, like we're talking about here, mean motion resonances here? Yes, okay. Yes, I mean, it's hard for me to tell how much effect a moon would have. I mean, if we consider the Earth-Moon system, the moon has a very large mass, in comparison to the Earth mass, but if you look at the distance of the Earth moon, it's still very short. So if there were an additional planet like Jupiter, and we had a resonant configuration of those two planets of Earth and Jupiter, let's say, and the moon would certainly give some little perturbation, but it's also beyond my knowledge whether the moon would really be able to destroy the resonance or not. I mean, resonances can be destroyed if you give a little kick to it. If you have an additional third object there which comes close, then you can destroy a resonance. Otherwise, it's very stable, as we see from Pluto and Neptune, or the Plotinus and Neptune. There are many objects in this resonance at the same location, basically, and they are all stable. But if another object comes, they can take all these objects of the resonance. But I doubt whether a little moon can do this so easily. Yes, this would be my answer, but I'm not an expert here.
I do have a question. What about the possibility of resonance trapping between the circumplanet and the divine?
Sorry?
Just a resonant case between the circumplanet and the divine.
Okay, yes. What about the question is, what about resonance trapping of the binary and the planet? That means that you have, this just like what I said here. In fact, the configuration I've shown here was a configuration 5-to-1 configuration. Okay, that's the whole point. These planets here like to be captured in resonances. Okay, but you will typically not reach the 2-to-1 resonance, because the 2-to-1 resonance would be very close to the binary, and the hole is bigger. So if you are captured here, that's also what simulations by Arno Pierens and Richard Nelson show, you can be potentially captured in higher order resonances. I think they saw 6-to-1, we saw here 5-to-1, and for a massive planet sometimes they saw also 4-to-1. Yeah, you are captured in a 4-to-1, and that means the planet does 5 orbits and the binary, the planet does 1 orbit and the binary does 5 orbits. This is what 5-to-1 means here. So we see this capture into resonances. Okay, but it can be shown, I think, from 3-body dynamics that the locations of these resonances are unstable in this case. This is an example of unstable resonances, not like the other case with Pluto and Neptune, which was stable. In this case, these resonances here are unstable around circumbinary. There are several n-body simulations where you calculate basically the time for escape of the planet of the system, and you can see, I think, that the locations of these resonances are stable. So why? That's what I mentioned here. Some planet evolutions are unstable, and then whatever, it may be unstable upon disk dissipation. So the disk is still there, and it damps a little bit eccentricity, but then you take it away, and then it becomes unstable. So, and all these observed planets are actually in between resonances, which is in agreement with this statement. So if they're really inside of a resonance, and during this migration process, they like to be captured inside of a resonance. This is the disadvantage here, yeah? But this would be an unstable configuration once the disk dissipates. Very similar to this scattering scenario for forming these inclined and eccentric planets. Yeah, so the disk, as long as the disk has very low eccentricity, it still acts as a damping agent, and when you take it away, you excite the eccentricity even further.